The next presentation is on EEnet verification of a multi-level DC-DC converter IC. Paul Denny was meant to be here. He called in sick, so Andrew Beckett is standing on his behalf. So I'm going to read out Paul's
Paul's
CV.
Paul wrote the paper.
Yeah.
I've only seen it this morning.
Yeah.
I've seen it before.
Yeah, okay. Paul Denny, he's from PSemi. He's a director at IC development. Okay. He's 40 years experience in the IC industry, managing mixed signal design teams on products ranging from CMOS fractional NRF frequency synthesizers, 10 gigabits per second DFE equalizers, and advanced power management ICs. There's a special interest in mixed signal SoC verification methodologies. And so does the person standing in for it. Well, I think you've got a few years experience on mixed signal. It didn't work for me.
Right, it might be okay if I do. No, okay, no problem. Right, so yes, so I'm standing before as Peter said. So I'm from Cadence, so not from PSemi, but we were involved, particularly Daniel and Tim, who were online, were involved with working together with Paul on this particular project. So thought it made sense that I was going to, rather than missing the presentation altogether, I'd stand in and try and do it. Actually, can I click on this one?
No, this
Okay.
I told you I'd break everything.
So, first of all, a bit of background on what is a multi-level DC-to-DC converter. Quick overview of the challenge, the verification challenge that's being faced, some of the limitations of traditional modeling methodologies, brief overview of EEnets, and then the key part of this is the accuracy and the speed that was gained from this particular project. So some of you may be familiar with a basic buck converter output stage. So the idea here is that we've got a switch, an inductor and a capacitor and some kind of load, and a voltage reference. And then what we would do is we would use some kind of pulse width modulation of that switch to essentially modulate what the output signal will be. And as we switch, you'll get a particular output signal that will gradually droop as the load drains current from the system, and you kind of have to keep re-topping up the capacitor to reset it over time. Now, of course, no one uses anything that's quite as simple as that anymore, so it gradually gets more and more complex. So we might move to using some kind of 3-level buck converter output stage, in which case we might have some kind of floating fly capacitor like this, and then 3 switches, in this particular 4 switches, sorry, in this case. If we work our way through, we will have, for example, this scenario where the fly capacitor is discharging, this scenario where the fly capacitor is charging, and you'll get different voltages. So you can see as I move through these different cases here, the voltage will be a different range, Vn/2. In this case, it will be also Vn/2 of that range. The output is 0. And effectively, what we end up with is 2 different bands. We can either have it in this band, where the voltage is in this range, or depending on the switch configurations, we can have it in this band where it's, again, we're modulating the switches appropriately to get a signal that way. So it means we can get anywhere between this overall range. Complicated bit is around the middle because you're kind of switching between the bands. And as we do this more and more, the digital control system for this gets more and more complex. Hence the need for a big verification challenge, because it's not just a simple pulse width modulator anymore with a control loop. It's going to be far more complex than that. Now, just to make it even more complicated, we might be using a 4-level buck converter output stage, which has got, in this case, 6 switches. And this has got 8 different states. Each state affects the capacitor differently, and effectively what we're storing is a Vn/3 of this one, 2 Vn/3 on that fly capacitor, and various combinations of these switches. Just showing one of them here. will give us, for example, the switches in this particular band, and there will be different combination switches in this band, different combination switches in this band. A much bigger, more complex control loop with lots of clever algorithms on the digital side that we're trying to verify to make sure it all works properly. So as I mentioned earlier on in response to some of the questions, the issue here is, we've got this big digital system, and to make sure it's going to work properly, we need the analog there, but we don't want the performance of the analog simulator to be the killer in terms of verifying the digital control system. So if we look at our verification challenge, in essence, the trouble here is we've got this large amount of digital RTL, we've got some preamps, and then we've got sigma delta converter in there, we've got our pods with modulation control, our ability to control these different switches, and the red part over here really requires some kind of conservative modeling. And by conservative modeling, I mean charge conservation, as we do in a SPICE simulator typically, for this to actually all function correctly. However, to simulate all of this on the left-hand side with this is going to take days to simulate in reality. And that was the big problem. It takes days to simulate, and you think, am I really covering anything? If I change the digital algorithm in some way, I've got to go through all that all over again. Am I getting the confidence that this is correct? So Paul wanted to find a different approach, explore a different approach, which might actually give him speed ups, but still give him the confidence that the digital is being verified correctly. So some of the limitations of traditional, we're using the word wreal here, which is the kind of Verilog AMS terminology for it, but single real number models where we are representing, we are using a more signal flow approach where it's event-driven time, but a continuous value, but you've got a single value representing our signals. So we might be, for example, representing this output of this current source as a real number, and that's going into this particular block here. The trouble is a port can only have a single real value, and so we can't calculate the voltage at this particular node. We can treat it as a current, or we can treat it as a voltage, or some other quantity, but we can't do both at the same time, which is what we need to do kind of a conserved signal model. So that's quite limiting. It's fine for many applications, because it's sufficient to do that signal flow modeling is absolutely fine for many systems, just not for this one. The other challenge is with the traditional single value real models, there were limited resolution functions. We could set, for example, some global resolution function, for example, wreal sum to add them up, but we didn't have much flexibility. And as was mentioned in the presentation earlier, using user-defined nets and types gives the opportunity for custom resolution functions. So in this particular project, Paul started off by looking at using the EEnet models. EEnets are a capability that we provide at Cadence, which employs SystemVerilog features, user-defined types, nets, and user-defined resolution functions. I won't spend too long on this slide because it's so well defined earlier on, but these are user-defined nets and user-defined resolution functions are an integral part of the language definition. And they allow any number of independent variables to be assigned to a port. So a combination of reals, logic, integers, etc. And those user-defined resolution functions that allow us to deal with a way to resolve multiple drivers on the same net. So if we look at the EEnet itself, this is a user-defined type which is modeled this particular way. So it essentially represents, in terms of a voltage source, a series resistance, and a parallel current source. Okay, so there's three fields in there representing that voltage, current, and resistance. There's a user-defined resolution function and a user-defined net that uses that resolution function in conjunction with the net. Okay. For example, we might have this resolution function here. So imagine that we've got three of these EEnets connected to the same net. We might have a 2-volt source with a 1K series resistance and a 0 current, 4K resistance 0 volts, and this one's got a 1 milliamp current, and that's a open on this side, so high impedance. And effectively what we can do is formulate the effective sum of the currents or some of the conductances, work out the output voltages, and so on, and give us this particular resulting EEnet value. This is covered in our rapid adoption kit, if you want to see more details. What about capacitors? So in essence, we can effectively formulate this as a difference equation. This may sound vaguely familiar from Peter's presentation just now, and essentially that can fit directly into this EEnet driver model. There's a similar arithmetic that can be done for inductors as well, and this provides an exact-ish solution equivalent to SPICE. The key thing here is we're representing this as a difference equation rather than a differential equation, and it's driven by an internal event clock rather than what SPICE does, which is to have dynamic time step control to basically try and minimize errors. As we've said before, you have to be quite careful with these kind of approaches to make sure you don't end up inventing yourself as a bad SPICE simulator, because a lot of work is going into SPICE simulators to handle error control and so on for the generic problem, and it's generally trying to solve differential equations. This we're trying to kind of do as the least possible amount of work to give us the best possible performance, and so we have to use this kind of approaches very carefully to make sure we don't end up having gazillions of time steps or ending up with instability. There is an EEnet library that we provide. Again, you do have to use these with a little bit of caution. These do have some modeling features to control convergence limits, time step control, and it covers many of the modeling needs. It makes adoption quite easy, but as I said, don't treat this as I could just throw everything together, it can just magically work. You've really got to think about the problems that Daniel mentioned earlier on. Try and make sure you're thinking about what it is you're actually trying to verify. Model to make sure you model exactly what you need to verify, not model everything you can. That's the danger. People get carried away and they try and do a waveform perfect model, which they really don't need for the purposes of verification of the system. So after a lot of work, so Paul himself did a bunch of work, and then Daniel and Tim assisted him with providing some guidance and some additional models. He was able to achieve an extremely fast speed up of his system. So it was a factor of 2,000 times faster than like-to-like comparison. So it means he can do his top-level system-on-chip simulation in minutes rather than days. This was a huge benefit in terms of finding bugs in the system and actually giving confidence that the result is correct. But as I said, it didn't come for free. It wasn't. There was a fair bit of work to get to this particular point. I was able to get actually extremely accurate modeling of the behavior. So this allows you to get high confidence in the algorithms, the system stability, and the functionality. And so that was something that was very hard to get if it was going to take you a couple of days to run a simulation every time. Am I really covering everything? And this with enough tests, both of AMS versus DMS, comparing the results, and then doing many more simulations on the DMS side, allowed you to Finally, just some pros and cons. So some of the benefits are that this can be, with care, very accurate, SPICE level accuracy for a carefully chosen problem. And notice here we chose to model the bits that had to be done in the conserved system and model those bits carefully, but not try and throw everything at this. We try to say, well, this bit makes sense to do an additional abstraction anyway. This bit could be signal flow. This bit, this is the bit we really want to focus on. But the challenges are it does require some expert modeling ability. This is, you need to be thinking about how do I manage my time steps? How do I, deal with convergence issues? Because this is the kind of model that it can all work. You do a simple setup and then you introduce some additional components, and all of a sudden it falls apart. So trying to understand what exactly is going on is not trivial. However, the payoff is great. There's a very wide range of abstraction possible. Your verification engineering really needs to straddle both the analog and digital domains to get the best of this. Huge system simulation speed. So you really want to be doing a top-down type approach here. And it also really requires it only requires a single simulation kernel, and which is obviously a licensing benefit potentially. That's not the main motivation. The main motivation was the performance rather than anything else. And this is not appropriate for everything, as Peter has said earlier. It's fine for this particular case, but I don't think you can run every analog system as a DMS model necessarily. And of course, you've got to think about who's going to lead the methodology in your mixed signals. So, any questions? I'm not sure how many are going to answer the questions on Paul's slide. Daniel might be able to answer.
I mean, if you were to have to redo this for every chip because it's bespoke for a different customer, do you think the ROI is there?
I think that if you're doing a set of similar kinds of projects, I think that's where the benefit. I think the knowledge and the approach to take is what has come out of this. If you were doing totally different designs every time, then it's probably, you're not going to gain that reuse necessarily. Daniel, I don't know whether you've got anything to add to that. You're still there.
Yeah, what we found is that in an organization, typically your next generation is mostly reused from the prior generation, and just like you can reuse the circuits, you can reuse the models. So there's definitely you do the investment once, and from then on it's just kind of tweaking and maybe one or two new circuits that need new models. It becomes very easy to catch up and keep up.
Yeah. And I'll add.
I will say that. Sorry to cut you off, Tim. There are things that you need to do from an organizational standpoint to make this kind of thing work better. It's everything from how you manage the models and who owns them, which Paul had on his slide here, to just basic things about how engineers draw their schematics. Very simple things like an engineer will have bits that she's not using, and so we'll just wire them to VDD or VSS. And when, let's say, you're using a more complicated UDN for VDD and VSS so that you can track voltages and currents around your system, and then you want to wire that into a logic input, that you're incurring some performance penalty by converting that complicated UDN into a logic value. Really, you should use tie cells. And so I've got a whole article on advice for avoiding things like that, but that has to be at an organizational level. You have to inculcate these kind of practices.
Yeah.
Go on, Tim.
On the ROI, this was something that could not be simulated. Like you said, it took days to simulate it. It couldn't be simulated where you got to see a lot of different views of the simulation because of the time delay. So this now allows them to run the simulations, get feedback quickly, and determine if it actually is working correctly with the digital, and if there's any problems like spec differences. Analog team designed it one way, digital team was expecting something else. That spec difference, if you waited until you were at the very end to find it, the ROI becomes very huge because it would either delay tape out or you'd find the problem in the lab. So ROI is kind of, if you find a problem, ROI is huge, right?
Lovely.
Okay.
Thank you very much.
Thank you.
Thank you. I think we have a break.
We've got a break now for half an hour, so you can go and cool down wherever it's cool.